In this lesson, we're going to talk about using the first derivative to determine intervals of increase and decrease. And again, this is something that we've already done. We just didn't give some of the names to some of the things we were doing. And so hopefully, if you didn't catch it the first time, this will help you out. And if you did, then hopefully you can just put the names to all of the things that we've been doing. So in this one, it first talks about critical values. This came up when we were studying for an exam. Critical values are just the places where your derivative equals 0 or your derivative does not exist. So when you find the zeros where the derivative is 0 or where the derivative doesn't exist, or your vertical and horizontal slopes, which is what we've been using that for, those values are our critical values. And those critical values are what we put on our number line so that we can determine the values of increase and decrease. So these are the steps we're going to go through. We're going to find the critical values. We're going to find our local maxes and mins, which will give us our intervals of increase and decrease. And then we'll review what we did in the lesson yesterday or the day before for the values that satisfy the mean value theorem. All right, so the first thing we need to do is to find the critical value, so it means take the derivative. So the derivative would be 1/3 x and then subtract 1, so to the negative 2/3 power. All right, and that is equivalent to 1/3x to the 2/3 power. We could set that equal to 0. If I set my function equal to 0, I would multiply both sides by the denominator, and I would end up with 1 equals 0, which is not true. But if I try to, and this is setting, let me label that, that's setting f of x equal to 0. But if I want to find out where f prime of x, but if I want to find out where f prime of x doesn't exist, that would be my vertical tangents, and so that would be setting this equal to 1/0, where the slope is undefined. Now, this one is super easy because we can see that's going to be undefined where the denominator is 0 and the denominator is going to be 0 at 0, but just for the future, it doesn't exist where the slope doesn't exist. And so 3x to the 2/3 power would equal 0. X to the 2/3 power would equal 0. And so x would equal 0. So we do have a critical value. Our critical value is where x is 0. So that would be part A. All right, for part B, we need to put that on the number line. We did have an interval given to us from -8 to 8. So on my number line, I only need to go from -8 to 8. Put my 0 on the number line. And then I want to test this out. So I'm going to plug in to my derivative. So I can pick any number I want. So I'm going to pick -1. And if I take the cube root of -1, oh, sorry, I was plugging in the wrong thing. If I plug in -1 to my derivative, I guess this would probably be the easiest derivative equation, -1 in here, then the cube root would be negative, square would be positive, so I get positive 1/3. If I put in positive 1 to the 2/3 power, I get 1 times 3, also 1/3 positive. So because this doesn't change sign, there is no max or min, no local max or min. Part C then asks us about intervals of increase and decrease. Well, this thing is positive the whole way through. So this thing is increasing from -8 to 8. All right, then for our last part, we're supposed to do our mean value theorem. And so for the mean value theorem, remember we're supposed to check for continuity. Is it continuous? And is it differentiable? Can you take the derivative everywhere? So for being continuous, this is the cube root graph shifted up 1. So it really kind of looks like the cube root function kind of turned sideways. This would explain why it's always increasing as well. But even if you didn't know, it is, you could pick any value, you can plug it in. But we already know that it is not differentiable everywhere because the derivative didn't exist. That's how we found our critical value. So since it's not differentiable, it does not satisfy the mean value theorem. So there's not going to be an answer to that portion. There's not a place on this graph that would be equivalent to the secant line slope. All right, on the back we have one more example. Of course, we need to try a trig example. So the first thing we need to do is find our derivative. So derivative of x is 1. Derivative of sine is cosine. So we have minus 2 cosine x. And so we want to figure out if there's any place where that is equivalent to 0. So 1 minus 2 cosine x equal to 0. 2 cosine x equals -1. Cosine x is 1/2. And cosine x is 1/2 is positive, first of all, in quadrants 1 and 4. And in quadrant 1, let's see here, on the 60-degree angle, we would have 1, 2, 3. So the cosine here and also in quadrant 4 with the 60-degree angle would both be solutions. So at pi thirds and at 5 pi thirds. All right, and then we also are supposed to consider where 1 minus 2 cosine x is undefined or doesn't exist. But there's not going to be any place because this is a continuous graph. So there aren't any gaps or holes like there were in, there's no vertical tangents like there were in the last one. So these are our critical values. There's our part A. All right, so for part B, we need to put those on our derivative number line. And our interval is supposed to run from 0 to 2 pi. So we're going to put our pi thirds and 5 pi thirds in between. And then we need to pick some values that we can solve for that are in between those spots on our number line. Okay, so I'm going to pick like pi fourths. So if I put pi fourths back into my derivative, I'd have 1 minus 2 times, and at pi fourths we've got 1 square root of 2, so it's going to be 1 over square root of 2. So 1 minus 2 over square root of 2. Now, without a calculator, all you need to know is that 2 divided by 1 point something is going to be bigger than 1. So this is 1 minus a number bigger than 1, which is going to be negative. Okay, in between, I think I'll just do like pi. So remember, pi is over here. We've got -1, 0, r is 1. So this would be 1 minus 2 times negative 1, or 1 plus 2, which is positive 3. And then over here, since I did force, I'll do high force again in quadrant 3. So that one's going to give me the same thing, 1 minus 2 times 1 over square root of 2. So 1 over square root of 2. So it's the exact same thing. That one is negative. All right. So just pick you some values and solve and see what you get on your number line. And so that tells me my intervals of increase and decrease. So part C was about increase and decrease. So this thing is increasing from from pi thirds to 5 pi thirds. And that's going to be brackets, not parentheses, not brackets. And it is decreasing on the outer intervals. So in this one, if you want to use brackets on the endpoints, you can. Parentheses are always okay on the AP exam. So if you're not sure, then just go with the parentheses. So increasing where it's positive, decreasing where the intervals are negative. Oh, you can see what I was writing. Increasing where it's positive, decreasing where it's negative. And then also, it had asked me on part B, I didn't really finish, about my maxes and mins. Well, if I'm going from negative to a positive decrease to increase, this is going to be a minimum. And this one's going from increase to decrease, so this one would be a maximum. So I have a local max, or a relative max, at x equals 5 pi thirds, and a local or a relative minimum at x equals pi thirds. All right. So for part D, we're supposed to check before you use the mean value theorem and see if it's continuous and if it's differentiable. And this one is a continuous function. It is differentiable, no sharp turns or holes or vertical asymptotes or gaps. So we can apply our theorem, and we have 1 minus 2 cosine x is our derivative equals, and then we're going to plug in our endpoints, and so we have f of 2 pi minus f of 0 over 2 pi minus 0. So we're putting 2 pi back into the original problem now, and so sine at 2 pi, so we're doing 2 pi minus 2 sine of 2 pi. Sine of 2 pi is 0, so this is just 0, so I just end up with 2 pi minus f of 0, so if I put 0 in there, that's also 0 and it's gone. And this would be 0 minus 0, which is 0, over 2 pi minus 0, so I just get 1. So I have 1 minus 2 cosine x equals 1. All right, so subtract 1, I have negative 2 cosine x equals 0. Divide by negative 2, so cosine x is 0. And the angles where cosine is 0 would be at the top and at the bottom, like at pi halves and 3 pi halves. 0, 1, 0, negative 1. So x could equal pi halves and 3 pi halves. So both of those satisfy the mean value theorem. All right, so that's a little bit of review of a lot of the things that we've already covered in our study in calculus so far. So hopefully it will solidify some of the things you already know.